Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, Abang and Prof. Taufik. Today, me and Grace, we want to present about our final project that has a title, Smart Chicken Incubator. We know that the farm, especially in poultry field, is need more than an efficiency. It is automacy and also the optimization of Internet of Things. Okay, so in this slide, we are containing about 5 meters contents, which is post statement, objectives, tools and materials, methodology and results, and also discussion. We see that the egg incubation really needs a precise of environmental control. But as we see, many of traditional systems that rely on manual methods that are not efficient or maybe inconsistent, and it is prone to the human error, which is called resulting into hatchability and productivity could be decreased or maybe reducing it. So when we see this problem, we must see that the intelligent automated incubators that are using sensors, microcontrollers, and all of real-time monitoring and precise regulation, it must be done to improve our efficiency, consistency, and sustainability, especially in poultry production. So there are five main objectives on our project, which is to maintain the stable incubation temperature, to automate the egg turning, monitor environmental conditions in real time, enable IoT-based remote monitoring, and improve efficiency and hatch success rate. With these five objectives, we are resulting in a project or a product that has been assembled, which is explained after this. But before, here are the tools and materials that we use in this project. For the tools, there are the SP32, the relay module, power supply, LCD display, breadboard, line and holder, fan cable, sensor DHT32, and also a microserver SG90. But for the materials that used in this project are scissors, tape, styrofoam, glue, plastic plate, Arduino IDE, Google Colab, chopstick, walkie, and also a ThinkSpeak as a part as the part of the software. Okay. So here are for the methodology. When we see this is the overview or maybe a review of all the process in our project. When we see the smart egg incubator, it is initializing with ESP32, the ESP32 LCD servo motor, Wi-Fi or IoT module, and relay system. When we initialize it, the the ESP22 will read the temperature and humidity of the environment in around it. When the when the DHT are success to read it, the the LCD display will also displaying the real-time temperature and humidity. And after that, when we saw that the temperature is exceeds 32.7 degrees Celsius, the fan on, and the heater, which is lamp, will be off. But if it below of it, the heater will on and the fan will off. And the system are run for several days, especially in 18 first days before in 19 until 21 days. It is the hatching period. So when the 4 hours already passed, we could see that the servo toggle position will be conducted. But if time hasn't passed for hours, it will be kept in current position. And with those process, the data will be sent into the IoT cloud, which is contains temperature, humidity, and fan or heater status. And finally, the whole progress could be done with the process could repeat continuously. Okay, so for the our smart egg incubator system overview, the core modules are ESP32, the ESP22, and the servo motor SG90. For incubation chamber, this is the image of our design, which is also contain the relay module, LCD display, and these all of the components are connected in IoT cloud platform in our phone. So we can control the whole process with the connected to Arduino IDE or the application in our phone. So it could be automated, monitored, and reliable and also efficient, which is we can also access the data anytime. Okay. So for the hardware architecture, we can see from this slide, the ESP32 are connected into five main components, which is LCD display, DC22, the relay module, and also the micro servo. This is for the simulation, actually, but the actual thing, it is connected into many components like fan, also lamp, and the other things that also could be displayed in the walkie simulation.
This slide explains the mathematical control model used in our smart egg incubator. The system uses programmed control rules to automatically maintain suitable incubation conditions for healthy embryo development. On the first section is the temperature control model. The heater and cooling fan operate based on temperature threshold, which is detected by the DHT22 sensor. When the temperature becomes higher than 37.7 degrees Celsius, the cooling fan turns on and the heater turns off to reduce excess heat. When the temperature drops below 37.4 degrees Celsius, the heater turns on while the fan turns off to increase the temperature. This condition they help to maintain stable incubation range between 37.4 and 37.7 degrees Celsius. And on the second section, it explains the egg turning function, and the eggs are automatically rotated every 4 hours. Between turning periods, the server remains in the holding position to maintain the tray stability. And this automatic turning process helps to ensure uniform embryo development and prevent the embryo from sticking to the shell. And on the third section, it shows the SG90 microserver rotation angles, and it rotates in 3 positions, namely 60 degrees to the left tilt, 90 degrees for the center position, and 120 degrees for the right tilt. And at the bottom of the slide, as you can see, there's a system flow overview. It shows that the sensor first reads the temperature and humidity values, and the ESP32 then applies the temperature and control the rules, activates the heater or fan if necessary, checks the timing condition, and control the servo motor for egg turning. So this process continuously repeats throughout the incubation cycle to maintain stable environmental conditions automatically. Okay. Moving on to the control system parameters. On this slide, it explains the operational parameters used to control the incubator system. These settings define how the system manages egg turning, temperature regulation, as well as the system timing. The eggs are automatically rotated every 4 hours, and this is done to prevent the embryo from sticking to the shell and to support uniform development. As for the SG90 servo motor, it operates between 60 degrees and 120 degrees to create the tilting motion of the egg tray. And the neutral of resting position is the servo, which is set at 90 degrees. And the system sampling delay is 2 seconds to stabilize sensor reading and ensure smooth system operation. The cooling fan activates when the temperature exceeds 37.7 degrees Celsius. Similarly, the heater activates when the temperature falls below 37.4 degrees Celsius. And also, our slide shows how the incubation is scheduled. It varies with the time and the days for the egg. So from day 1 until day 18, egg turning remains active to support the embryo growth. As for day 19 to day 21, egg turning is stopped because this is the hatching period and the movement may disturb the chick during hatching. And these parameters allow the incubator to operate automatically with minimal human intervention. Okay, so I'll also explain about the egg turning mechanism. So in this case, we use the SG90 microservo motor to rotate and tilt the egg tray automatically. The servo receives control signals from the ESP32 microcontroller and operates using an external 5-volt power supply for stable performance. The servo rotates between 3 positions, namely 60 degrees for left tilt, 90 degrees for the center position, as well as the 120 degrees for the right tilt. So this movement, it creates a gentle rocking motion of the tray, the egg tray. So our tray tilts left and right every 4 hours to simulate natural egg turning performed by hands. And this process is done, and it helps to improve the embryo development and prevents the embryo from attaching to the inner shell membrane. And based on the days and how this mechanism works, from day 1 to day 18, the turning will be active. As for day 19 to day 21, turning of the eggs is automatically stopped to avoid disturbing the chicks. Okay, and also on this slide, I'll explain about the IoT cloud integration used in the smart egg incubator system. So the ESP32 microcontroller connects to the Wi-Fi and sends real-time incubation data to cloud platforms through the internet. And it begins with the incubator system, where the DH222 sensor measures the temperature and humidity condition inside the chamber. And the ESP32 process this information and transmit through a Wi-Fi router to the cloud platform. In this project, we use the ThinkSpeak for data logging and graphical visualization, while the Blink is used as a mobile monitoring dashboard. The system sends several important parameters to the cloud, which includes the temperature, the humidity, heater status, fan status, server activation, incubation day, as well as the timestamp data. Through the mobile dashboard, users can remotely monitor the incubator in real time using smartphone or a computer. One of the major advantages of this system is that it can access environmental conditions from anywhere without needing to manually inspect the incubator physically. And these pictures, they demonstrate how embedded systems and cloud technology can be combined to support smart agriculture and automated poultry farming. Okay. So on this slide, this is our smart egg incubator that we designed. And the incubator chamber was constructed using styrofoam material because it provides a good thermal insulation and help to maintain stable internal temperature conditions. As for the side view, we can see that the external hardware components, including the cooling fan, the wiring system, and the ESP32 connections and power supply arrangement. And the top view shows the internal structure of the incubator, including the heating bulb, the cooling fan, and egg tray placement inside the chamber. And during testing, the system successfully maintained the incubation temperature within the targeted range, approximately 37 to 38 degrees Celsius. The heater and cooling fan operated automatically according to the programmed temperature threshold, and the DHT22 continuously monitored the temperature humidity conditions while the LCD display read and display the real-time environmental data for the local monitoring. The ESG90 server monitor also functioned successfully by rotating the egg tray automatically at 4 hours interval. And in addition, the IoT successfully transmitted real-time data to the cloud platform and mobile dashboard for remote monitoring. So our project demonstrated stable environmental control, reliable automation, and successful integration of embedded system, sensing technology, server actuation, and IoT communication. So that's all about our project. Thank you.